All right, we're going to get started here in just a couple of minutes. We're in about a minute or two, really. Seeing a lot of familiar names joining in here. All right, 3:02. Let's get crack-a-lacking on this Friday afternoon here. Good afternoon, everyone. My name is Randy Persaud. I am HPC staff here at the University of Alabama, and today I'm going to be giving you guys a brief introduction on utilizing UA's HPC resources. And so I'm going to talk a little bit about UHPC and CHPC cluster. I see that we have quite a diverse audience. Some of you conducting research on these clusters and some of you who I believe are totally new to HPC. So hopefully this talk will cater to people of all backgrounds. So for a lot of you guys, some of this information may seem redundant or you may know this, but hopefully as we get to the later end of the presentation, I'll be covering some new material or stuff you haven't seen before, things that are useful. So with that being said, let's go ahead and jump right in. So I'd like to start off with, okay, that's sharing, cool. I'd like to start off with the University of Alabama Research Initiative message here. And the goal of UA's research is to pursue discovery and dissemination of knowledge through research, creative scholarship, and technology transfer that impacts our students, our state, the nation, and the world. And so we aim to accomplish just that through our HPC resources. Well, first question is, who are we? So meet the team. Spearheading a lot of our HPC research efforts is DJ. He's the executive director of research computing and networks. Fun fact about him is he used to work for Intel at Silicon Valley. Second, we've got Robert Griffin, sysadmin. If you ever submitted tickets, it's either myself or Robbie that's usually answering them pertaining to HPC. Robbie's got his hands involved in so many other projects, not just working with the HPC. Also, we have Luke. He is a GIS programmer. GIS is essentially geographic information systems that goes into things like looking at mapping data, things for weather patterns, disaster management, managing resources, things like that. And then you have me, yours truly, Randy. I am the HPC cluster engineer data scientist. Pretty much I help you guys utilize HPC resources. And yeah. So I mentioned HPC a couple of times. So what is HPC? I believe most of you guys, this audience would probably know what HPC is, but for those who don't, let's take a step back and compare it to a typical Dell desktop computer, or a typical computer really. So for a typical $1,500 computer, you'd probably get half a terabyte, 512 gigabytes of storage. That's your SSD. About 16 gigabytes of RAM. That's how well you can multitask. And then for your CPU, you typically have some kind of i7, some Intel chip, or maybe Ryzen, AMD. And that's typically 4 to 8 cores with a clock speed anywhere between 3 to 4 gigahertz. And what I'd like to introduce to you guys is this idea of floating point operations per second, or flops. And we can calculate that by just taking the clock speed of the CPU, multiplied by the core, multiplied by the number of operations that can be done. That's typically limited to the instruction set. So the latest instruction sets give us about 16 operations per second. And so that's how we get kind of roughly 336 gigaflops of computing power, or 0.35 teraflops of computing power a desktop would have. And most of these desktops either have some kind of integrated memory, integrated video or a dedicated video card for visualization purposes. And so these desktops are used for typically handling your, your day-to-day workloads, things like checking your email, video calls, Microsoft Team meetings, PowerPoint presentations on Zoom. And, that's enough to do all computing workloads, right? Well, wrong, not exactly. If that was true, then I'd be out of a job and you guys probably wouldn't be using HPC. We have problems when we look at big and small, issues. So if we're trying to look at, something on a global scale, that gets really expensive. If we try to look at something small in great detail, that also gets very expensive as well. I'm sure, as this audience knows, when we're doing research. So how can we tackle that if we can't run it on a typical computer? We turn to HPC, high performance computing, or cluster. The terms get used interchangeably. But as you guys know, this is the aggregation of computing power to solve large problems across various fields, whether it be in STEM. You can even branch out into art and business and projections, economics, and things like that. And so the idea is that, you imagine tens, hundreds, thousands of desktops working together to complete one job. It's a gross oversimplification, but that's kind of what's going on here. Where you, the user, logs into a computer, then that computer tells other computers to do the heavy lifting, and then you get your information back out, and then you can save it, store it, work with it, do post-processing. That's kind of the idea. And so these individual desktops, you can sort of think of them as nodes, and these multiple nodes work together in tandem, and that essentially makes up a cluster. And so the relevance of HPC has been seen throughout the years. This graph here on the left, on the y-axis, you just have the computing power in log 10 scale here. And on the x-axis here, you just have over the years. And as you can see, over the years, aggregate computing power in the world has been increasing. And if I get rid of the log scale, you'll see that it's actually really exponential, and it's been exploding in the past 10, 20 years or so. I'd imagine there might be a little bit of a plateau here due to, the pandemic and chip shortages. That's a whole other topic of conversation. But I think you get the idea that, in the past 20, 30 years, computing power has just exploded. And I won't spend too much time on the background of HPC, since I figure the audience here has a good idea of its relevance. But just to show you guys that, throughout the years, in the 70s, weather forecasting done by, the Cray 1 supercomputer in Los Alamos National Lab, being able to, forecast weather predictions and things like that, important. In the 80s, looking at radiation shield modeling, probabilistic analysis, was done by this CDC cyber machine. Fun fact, that machine was also one of the first machines that learned how to play chess. So it was the first chess playing supercomputer, one of the first. But that, being able to design materials that can withstand radiation in space. In the 90s, DS cracker, thanks to this HPC here, we were able to, the DS encryption was broken, and then now that's what we have RSA 248 and other encryption standards. In the 2000s, we have nuclear test simulations that were done by the ASIC-Q system. That was also at Los Alamos, just to understand, trajectory explosives of nukes and how they can be used, and how could they be used in not war scenarios, I guess you could say. And then in the 2010s, MD simulations really kicked off. The Human Genome Project essentially was finished, and Human Proteome Project of great interest. But also, a lot of silicon studies were also done as well. That's what the Tahi 1A cluster in China was used for primarily. In the 2020s, kind of now era, drug design, outbreak prevention, electrochemical reaction research, that's akin to, coming up with new batteries and cells for these hybrid vehicles. And just throw big buzzwords out there: AI, ML, artificial intelligence, machine learning, that kind of stuff is what's relevant in this decade here. So anyway, that's the relevance of HPC for past century or so. So let's go ahead and dive into, well, the hardware of HPC. What do you guys have access to here at UA? So what's under the hood? Well, the first cluster veterans would know is the UA-HPC cluster, the University of Alabama High Performance Computing Cluster. It's a 56 node heterogeneous cluster that was kind of built using the condo model. And the idea behind the condo model is that this cluster grows as you researchers either buy nodes for it or as you researchers buy nodes for it. And the idea is that as you buy nodes, you get priority on running on those said nodes, and other people can use it as well when it's not in use. And that's how that cluster grows. And so currently right now, has over 1,700 CPU cores with a mix of GPUs, 2 NVIDIA Voltas and 1 Tesla 1T4 GPU. And again, it's a heterogeneous cluster, so the nodes are comprised of different models and SKUs. Right now, the cluster stands at 64 teraflops of theoretical CPU performance, plus an additional 177 teraflops of GPU accelerated performance. And then for the second cluster, we've got the CHPC cluster, the Cyber Infrastructure High Performance Computing Cluster. This cluster was built, was awarded to us through the Campus Cyber Infrastructure Grant from the NSF. And you can sort of think of this as a grant-funded model type cluster, where we received an award of $350K, and we used that to purchase the cluster. And so we're working on more NSF grants to purchase more hardware. This is a 32 node homogeneous cluster since it was all kind of bought all at once. And it's right now rocking over 2,000 CPU cores with 5 NVIDIA Ampere GPUs. This cluster has 80 teraflops of theoretical sustained double precision performance, just CPU, plus an additional 3,120 teraflops of GPU accelerated performance. And so just to show you a snapshot of what kind of this ecosystem looks like is that either you're an external user connecting to the UA high-speed network through a campus VPN, or you're here on campus, you're able to connect to the internet, the network. And from there, users are able to either log into the UA-HPC head node or the CHPC head node. And depending on which server you log into, you have access to said nodes, and you're able to submit jobs to these nodes. And as these nodes process your job, your outputs get stored in our Parnassus storage, which is comprised of a home directory, big home directory, and Scratch, among other things. But for this introduction, we're just going to cover these guys here. In your home directory, you have 50 gigabytes of storage per user. In your big home directory, you have about 500 gigabytes of storage per user. And in your Scratch directory, you have about 2 terabytes of Scratch to play with. And in addition to all of this, there's also a data transfer node if you just want to pull your data off of the Parnassus storage here. So that's kind of the hardware side of things. And so let's just quickly dive into software. And to put it simply, we've got a lot of pieces of code installed on the cluster. A fair chunk of it may not be used, but this image here kind of just shows the breakdown of what we have. And as you can see here, that a large chunk of it is biological sciences. That doesn't necessarily mean that the cluster is used primarily for biological science type work. It just means that that a lot of the codes for biological sciences are still in development, or there's a lot of like small codes here and there where there's like parsers and splicers and things like that. And so we typically get a lot of small codes like that installed. And then for engineering, physics, and chemistry, that's typically stuff like, Gaussian lamps, MATLAB. That stuff doesn't change really. So except for, every year if a new iteration or version comes out, we update it. But that's the reason why the slice seems smaller. So yeah, we have over 400 pieces of code installed in various ways. Either it's installed through pip, conda, or through traditional means. We work with researchers to get the code installed We're also updating the OIT website, which will contain updated training videos. One of our goals is to have a searchable research software list where if you can like truncate it by like have like a filter, like you want to see only physics-based software, you can check the box and you'll see all the codes that you have installed. And the idea is that you click on, lamps or something, and then it'll show you, it'll bring you to another page where it has lamps, how to load it in, an example job submission script, something like that. So that's the ultimate goal, and we're still working on that. And then there are more things we're adding to the website as well, like the status of the cluster and things like that. And so you may ask yourself, how can you access HPC resources? It's really quite simple. The URL is hpc.ua.edu. And then everything you'll need to create an account is clicking on this UAHPC portal button here, and your help and support is down here as well. And so if you want to utilize HPC cluster resources, you can visit the website. You click on the button, you sign with your MyBama ID, it's the same credentials, and then you can follow the prompts to request an account. At the bottom, I do ask for you to specify what kind of codes you might be interested in running. That'll help us put you in the correct group. There's also a checkbox for signing up for the Blackboard course, which will give you access to training videos and running on the HPC. And yeah, the rest is pretty much self-explanatory. For those who've already have an account, you log into the cluster, you run your jobs, you collect your data, and you're good to go. So yeah, once you've signed up, what to do? UHPC CHPC uses the Linux operating system. It runs specifically on CentOS. It's an open source Linux distro that's kind of based on Red Hat. That is based on Red Hat. You can connect to the cluster via SSH protocol, and you can use anything from PuTTY to Unix to Windows PowerShell. However, I do tend to recommend to use something like MOBA Xterm or Xquartz, since that it allows forwarding of GUI applications through X11. If not, some researchers have done workarounds by launching, VNC servers and stuff like that. That works fine too. The host names are uhpc.ua.edu or chpc.ua.edu. And your login credentials are, of course, the same as MyBama. And if you're off campus, make sure to sign up for the Cisco VPN or register for the Cisco VPN. And then you submit jobs using Slurm. So what is Slurm? So Slurm stands for Simple Linux Utility for Research Management. See, the thing is, we have a lot of users with different resource requests using this cluster. And so it becomes a balancing act on, who has priority, what types of jobs you're able to run before others, things like that. Because there have been periods of time where, one person batch submits hundreds of jobs, but that locks out, in theory, it would lock down the whole entire cluster. But we use something like Slurm that help us balance out the maximum amount of jobs someone could submit with the amount of resources they can utilize. So Slurm is free and open source job scheduler for Linux and Unix kernels. It's very popular. I would say it's probably more than 60% now, but it's used by the top 500 HPC clusters. It allows allocation for exclusive and non-exclusive access resources like CPU, memory, and GPU via QoS and partitions. QoS stands for quality of service. And for QoS and partitions, I'll go into more detail about that, but just know that you request to run on specific QoSs and partitions or combinations of them to have access to certain resources. Slurm provides a framework for parallel job management for starting and stopping and monitoring jobs via MPI, which is Mrs. Bash's interface. It's basically how cores talk to each other, nodes talk to each other. And the idea is that, we have fair sharing and research management through accounting capabilities through Slurm. And so if you're part of a group, the group has some amount of priority. If a particular group is using a lot of resources and then, another user logs in who hasn't ran in a while, they may have more priority over the group that's been using the cluster for quite some time. So here are a list of some useful Slurm commands. So Slurm is used for controlling and queuing running jobs. Jobs only run on compute nodes. And so I'm sure some researchers have experienced this where they may have accidentally tried to run a job on the master node or the head node. we have to manually intervene and kill those jobs. And Slurm does not schedule jobs on the master node. So it's usually someone accidentally not realizing that they're running something resource intensive on the head node. So we try to be active about that and we try to limit that. SBatch is the command that submits the job. And so it's usually SBatch, and then you filter it in your job rules, some file that contains the rules for the job, or you do SBatch and then a job rules. And then there's the SQ command that shows you what is running. I'm going to see if I can. There we go. I have a terminal here pulled up. I'm already logged into HPC just so I could show you guys. Actually, let me leave it like that, split, so you can still at least see the command. Yeah, so SQEU shows all the jobs that are running. As you can see here, UHPC is kind of booked. Shout out to this user here. So here you could see all the jobs that are running. If you want to truncate the jobs that only you are running, I'm going to pick on this user. I'm going to pick on Gabriel. So if you want to see a job that only you are running, you can do SQEU and then your MyBama username, like so. And you can see that this user is running these two jobs here. And then another fancy command that I really like. Gabriel, I'm going to pick on you some more. Slurm top. The Slurm top command it's a very nice image that kind of shows you what's being utilized on the cluster. I'm typing C for the number of columns. I'm going to set it to 2. So it's kind of squished like this. And you could see this is kind of a visual representation of what's going on in the cluster. These nodes here might be booked in terms of like whatever is being used on here. Probably, they're probably requesting a lot of memory. Hence why this is probably not being filled up all the way. But you could sort of see it's kind of color coded based off of the job. And I'm going to, I type U and then I put in a username. I could see that Gabriel here, his jobs are running other MoPro jobs. So probably their high memory jobs are running on these nodes here. So it's a nice visual aid of, kind of what's going on live in the cluster. And then if you want to kill a job, it's just cancel and then your job ID, which I'm obviously not going to kill that job. But yeah, so some very useful Slurm commands there. If you wish to load software, we no longer use .kit. So for the veterans, back in the day, we used to use .kit to sort of load what I guess we call modules now. So we no longer use .kit. I believe we've transitioned all the .kit files to their module equivalent. If we may have missed one, or if there's something, if you need a .kit file converted or something, just get in contact with us. We'll help you through that. So yes, now we use modules to load packages. And so again, I'm going to pull up my terminal here. I'm going to make this a little bit bigger. Okay, I'll just clear my screen. And so the command we'll see all the modules that we have available is module avail, pretty simple. It lists all the modules. So as you can see, we have bio modules, Miniconda, math for your MATLAB, different versions of MPI if you want to compile codes, so on and so forth. Space, space, space. Blow this up like that. Space, clear. There we go. So we have a large sample, various types of codes. And if you want to truncate it to just seeing compilers, for example, you could do module avail compilers like so, and then it lists, all the compilers we have here. So, and then of course to load a module here, it's just module load and the module you want to load. In this example here, it's GCC, but I'm going to go ahead and preemptively load Gaussian. And if you're curious to see what really goes on in a module file, this is, for example, the Gaussian module file. And all it does is it sets up environment variables. It prepends to your path, in this case here, the Gaussian program. It also adds a script folder to your path. And it also prepends the executable for launching the GUI for building Gaussian molecules or Gaussian jobs in your path as well. And so just simply by loading that, I now have access to the files that are that directory, which are these scripts here for running Gaussian. So, all right, let's head that over here. So yes, this can be used inside an SBatch file to load prerequisites, source files, prepend paths, things like that. Some programs with initialization files will tell you that you need to run it with instructions on what to do. Certain kind of environments will require this. It's just going to be a pop-up. If you try to load a module, it may warn you saying, hey, you may need to load something additional depending on your situation. Let's see here. Okay, so I mentioned, this SBatch file. Here's an example of an SBatch file. So again, the command to submit a job is SBatch, and then my job rules, or the name of SBatch and the file that contains essentially this information below. And so it starts off with a shebang. We specify bash, and then here are your SBatch commands. So SBatch tac end1, that's the number of tasks you're requesting, and the default's 1 CPU per task. So this is a single core job. And then tac j, then you could specify a job name. So if I go back to say here, SQ, your job name will appear pretty much in this column here. So this test, or whatever you want to call it. Let's see, we've got tac P and tac QoS, partition and QoS. I'm going to dive into a little bit more about this later, but this is where you're requesting what partition and QoS you'd like to run in, what you want your error files to be named, what you want your output file to be named, time. So maximum amount of time you're requesting for this job to run. In this case here, it's 10 minutes. And then this goes back to the idea of you can load modules within these SBatch files. So after this last SBatch command, these are the commands that are going to be executed on the compute nodes that your job lands on. And so in this case here, it's going to load the Python module, and then it's going to run whatever Python script this is, for example. To look at something a bit more complicated, let's look at lamps. So again, very similar, well, somewhat similar setup up top. SBatch, tac j, job name, number of tasks, so about 32 cores. This tac capital C now is a constraint option. This limits where this job could run. So to my understanding, this version of lamps here is actually an Intel compiled version. And so we kind of want to limit it to nodes that have Intel chips. So that's why in this SBatch command, we put tac C Intel to limit it to Intel chips. And then next we have memory per CPU. So here we could specify we want 5 GB of memory per CPU. And then again, partition QoS, main, what to call our error files, output files. And then if you want to be emailed the status of your job upon completion, you can use this command as well. And then here's the command to submit lamps. And prior to this, you could load the module here, or you could have put the module inside your SBatch file. We do recommend only running the Intel version of this. I think the other compiled versions might be a little wonky, but the Intel works pretty solid. Here is another example of SBatch using Fluent. Same kind of idea: job name, number of tasks, partition, the QoS. Here you're going to need to concatenate your host name for Fluent to see it. You don't want the GUI of Fluent to launch, so you can export that variable and tell it not to. And then here are the commands for running Fluent. And then to clean things up, there's a remove command here at the bottom. And so, depending pretty much what's above, pretty much kind of above where my marker is pretty standard stuff. What's underneath is usually unique to said code. And so that's what we help, we work with researchers on, is how do we get this bottom half of the job submission script to work, or how do we manage this workflow essentially. And then there are some modules you need to note load as well before you launch Fluent. And these could be put inside, right after the sbatch command, or you can load them ahead of time. And then we also have a threaded partition and QoS. And so instead of running on per CPU, you can utilize the individual threads on the CPU themselves. And so there are pros and cons to using threads as opposed to cores in terms of, task switching and things like that. But if you want to run on threads, they're very fast. You can just request to run on the threaded partition in QoS. Again, what's above, what's the sbatch commands are pretty standard. It's just that you're running on the threaded partition in QoS. The threaded partition has 80 fast cores, and you can run jobs up to 2 days, but limited to 16 cores per job. And I know a fair bit of researchers also use MATLAB. Here's an example with MATLAB. This stuff up here is pretty standard. Down here, you have your the code that you like to run here, and you essentially run MATLAB. No GUI, no desktop. Don't need the splash screen. You could just submit it as is. Of course, with MATLAB, as well as other programs as well, there are actually multiple ways of running these jobs. Let me see if I can pull this up here. Here we go. We do have documentation on the HPC website about running MATLAB on HPC. This is kind of the example I'm showing in my PowerPoint slide here. Let me make that a little bit bigger. But if you want to launch the GUI on your desktop, and then connect to the cluster from there, we do have an example of remote usage using the parallel computing toolkit in MATLAB. And here are pretty much the instructions for doing so, and some common problems in case you run into some issues. And then we have GPU nodes for UHPC. Let me get that laser pointer back up and running. For UHPC, we have a 16 gigabyte and 32 gigabyte Volta V100 GPU plus a 16 gigabyte Tesla T4. We have a mix of GPUs on UHPC, essentially. And on CHPC, we have those 5 GPU cards in there. And so if you want to use the GPUs, you want to make sure to specify sbatch GRES, which stands for generic resources, and then GPU:1 to essentially run on any GPU that's available. And then you also want to make sure your partition and QoS are pointing to GPU. If you want to reserve a very specific GPU, you can, for example, reserve the V100 by saying GRES GPU:V100. But keep in mind that you must have software that can utilize a GPU in the first place. So not all GPU capable jobs are suitable. It depends on the code. There might be a flag you need to turn on when you compile it. It's a case-by-case scenario. If you have a model with a lot of data that must load into the GPU, it may be faster to run on the CPU instead. But we have seen speed ups with LAMPS and MATLAB. There is a GPU-enabled copy of LAMPS. I'm going to switch back over to here. Clear this guy, module avail. I think it's down here. So we have a GPU build of LAMPS available for those who are running LAMPS. Right there. So if you want to compile your own code, you'll have to get an interactive session on the GPU node. And you can do that there. So Interactive, yeah, so you could do that there. I just mentioned interactive jobs. So there are different ways to start jobs. You can use srun or salloc for interactive jobs. The difference between them is that salloc allocates the resources but doesn't start the job. So if you do salloc and then say, tac p and then, specify all this stuff here, you'll still be able to use the terminal. You'll still be on the head node. But then since you're having a job technically running on a compute node, you can SSH into that compute node. And then srun allocates the job and then starts it immediately. So let's see if it'll let me do that. Let me just, let's have an srun example here. There we go. So, srun immediately throws me on compute 4-5. But if I oh, look at that, 4-5 is actually ready to go. So if I wanted to, I could log into 4-5. So that's essentially the difference between the two commands. All right. To run on one or more core, yeah, you could, it's pretty much self-explanatory. To run on one core with xterm, you could do srun xterm. To run MATLAB in interactive mode, this is going to be a bit sluggish because that GUI is pretty hefty to load, will require a bit of memory. You have to load the MATLAB module, but then you can do, srun and then launch MATLAB that way. And then, of course, if you exit the session, it'll end the job and free up that node for other people to run jobs on. And then we have many options and variations. As I mentioned before, there's something called partitions and something called QoS. The partitions or TAC-P option is a collection of nodes that are categorized into main, long, threaded, GPU owners, high mem and stakeholders. High mem and ultra high. So inside these partitions, you also specify QoS to get either 24 hours of runtime, a week, time to debug, or specify your specific owner's group. And so the 24-hour queue is called main, 1 week queue, QoS is called long. The 15-minute QoS is called debug, and the 48-hour threaded QoS is called, threaded. And then if you're running MPI, you have 3 different flavors. You can use MVA PICH, Open MPI and Intel MPI. Most people, I believe, use Intel MPI or Open MPI. And we still have this command, use tac L, to list all the software options. But it is a little bit outdated, and I think that's coming from .kit, but that's still there. To memorize all the QoS and partition pairing is a little confusing or daunting. So I made a table, I think, that summarizes it quite well, of your pairing of your QoS with your pairing of your partition. So the column here is just the different QoSs, and the rows here are the different QoSs, and the columns are the different partitions. And so if you're running on main, your limits are 24 hours at 1,500 jobs per group. Or if you're running on threaded, your time limit's 48 hours, 80 cores per group, 16 cores job. It's pretty self-explanatory. Where things get interesting is the owner QoS with the owner high mem or ultra high partitions. This really is a case-by-case scenario depending on, the owners. But yeah, those are dependent on the purchase hardware, unlimited time, and you also have the ability to preempt other jobs that are using those nodes, that are on the long and main QoSs. This is, sorry, I forgot to mention, this is for UA HPC. For CHPC, it's a bit more simple than that. Again, same kind of idea. Your rows and columns This is your pairing between, main and long, high mem and debug and things like that. And so we have 10 minutes left, so I'm just going to fly through the rest of this here. Here's some tips for efficient use. Don't specify the number of nodes, TAC n, unless you're restricting to one node. Flexible scheduling is going to be most efficient. Your jobs are going to pick up faster that way. Consider memory requirements. The main partition has a default of allocating 1 GB of memory per core. You'll probably want to increase that if you're running MPI. Large core count MPI jobs might need even more memory. And you should also consider your job. If you increase grid size, increase memory. And then you can check memory usage after a job finishes with SACCT. And so the command for that is SACCT, TAC J, and then your job number, and then format, and you can specify a max RSS. If you know your job will use less time than the partition or QoS limit, then use the TAC T option. That way the scheduler knows that you're probably not going to use the full 24 hours to run a job, probably 10 minutes. And by specifying that, your short jobs may actually run sooner if they can backfill on empty nodes that are being saved for bigger jobs. So pretty self-explanatory there, right? You don't want to request 24 hours for something that may take a minute or two to run. Otherwise, your job will be treated as if it's going to use up 24 hours. And so if a big job has been waiting to run for a week or so, that job may not have a chance to squeeze in there. And of course, you could check how long a job previously ran in real time with this SACCT command here. There are some more tips as well. Again, don't ask for more resource than you need. Of course, one of the biggest challenges is how much resource do I need? And that really depends, of course, on the job, the memory, the size of your calculation, how efficient the code was compiled, numerous factors. But you could always look at your finished jobs with SACCT. Here are more commands that showcase what SACCT can tell you, CPU time, memory, things like that. But this kind of shows what was used after a job is completed. Let's see. Yeah. This S account here actually allows you to list all the jobs. Instead of me telling you, why don't I just show you? There we go. Let me just show you. One second here. Let me. Just like that. Sometimes it pastes funny from PowerPoint, That's much better. Okay, there we go. So this command here just showed me, all the jobs that I've ran since this date, for example, and it shows, what's completed, what's failed, what partition I ran on, state, time, and then we could always tack on more parameters here to get, a better idea of, see if I add CPU time at the end there. There we go, CPU time here, for example. So it's very flexible. And then if you want to see usage of a running job, you can use the stat command instead. So this kind of gives you, so here you don't have to wait for the job to finish, but you can use stat, TAC-J, the job number, and then you could get information about a job that's currently running right now. If you need to run a job quickly just to see if it'll work, there's a debug QoS that's useful for testing jobs. It does have a low time limit, but jobs will typically get into the queue much faster. The time limit will leave is 15 minutes. You can check your setup often more quickly using the debug QoS if you tried to use another partitioner QoS. Another really nice command is this sinfo command as well. I'm going to go ahead and fire that guy in there. And so just the %20 and %10 just controls the amount of characters that's displayed in the column. But this here shows the lists, this here lists the nodes that we have on here on your HPC, but the amount of CPU that's available, the amount of memory, features. If you want to use, if you remember back, we talked about tax C, capital C for constraints. You can put in a constraint for running on, this type of node. And that way the C6 for 20 nodes, only these guys here will be picked up by your job, for example. And if there's any special GRESS parameters you can specify, like for example, if you want to run on the GPU nodes, you could specify GPU T:(T4:1 if you want to run specifically on this Tesla 4 GPU node. And then we also have the scontrol top command here. And the idea behind this command is that I'm going to jump back over to the terminal. SQ. Say this gentleman here who submitted a lot of jobs wanted, say, this job to run next. So as soon as one of his jobs are finished, he wants this job to run next for whatever reason, even though he didn't submit it chronologically to be the next job. You can do scontrol top and then that job number, and that this job will, if it can, pick up next. So instead of you having to cancel or hold or requeue jobs and things like that, the scontrol top command's got your back there. And then the last tip I have for you guys is that there's a command called UA quota. UA quota, like so. And this shows you your usage quota in Parnassus. If you recall, for the Parnassus storage, you have a 15 gigabyte storage limit in your home directory, half a terabyte storage limit in your big home directory, and a 2 terabyte limit in your scratch directory. So the UA quota command here kind of shows you where you stand on those things here. And so I know I covered a lot of information very quickly, but that's all I have for you guys today. If you have any questions, this is the HPC website, .ua.edu. Feel free to ask questions or software requests or request accounts through there. And I'll be glad to help you guys. So I see we have a lot of chat activity. I didn't get a chance to check the chat during the talk, but if you guys have any questions, shoot us an email, shoot us a ticket. We're glad to help.
Hey, Randy, we've gotten a lot of requests for today's material, so I made a note that we could export the participant list and share some resources with everyone next week.
Oh, absolutely. Yeah.
And then we've had a couple of technical questions, but it seems like Robbie's done a good job answering those.
Yeah, Robbie. So I actually started last August, so I'm actually a fairly new hire, but Robbie's the vet here. So he's he knows these systems inside and out. I actually started off as a graduate student here at UA, and I worked with UHPC for quite some time. So, but yeah, any other questions? All right. Well,
excuse me. I have a question.
Yes.
So the software which we want to run, it should be installed in the HPC, right? Suppose I want to run a software named Liu Medical. Can I run in HPC system, or do I have to install it or something like that?
Well, we try to keep things, nice and tidy. We do have a share apps directory here. I'm still screen sharing, right? Yeah. And if I list here, you could see all the folders and stuff like that. We have people who've installed their own codes in their own home directory. That's fine. The most important thing is that you don't run on the head node. So whenever you do submit your job, you submit it through Slurm for the job to run. And then secondly, your code may take up, some of that precious, storage on your home directory. So, but no, if you have your code installed in the home directory, that's okay, as long as you're submitting it to through Slurm for the job to run.
Okay. No, I'm saying that suppose people using MATLAB, people using Python and other softwares, something like that. So if I want to run a particular software, which is not here, I mean, not in your HPC, in that case, what?
Sure. Yeah. So you could install it yourself. You can request us to install it. We can give you a directory in here for you to install that piece of code into. I mean,
Okay.
it depends on licensing too. We have to take that in consideration. Like I believe VASP, you'll need to only certain users are registered to use VASP. So we may have to create a special group that are like VASP users, for example, or whatever that code is, for example, that can only use that code. But no, you would message us, what code you want installed, and we would work with you on that. And if you need help coming up with, some kind of workflow, for example, on, how to set up the job submission, we'll definitely help you with that as well.
Okay, thank you. Thank you very much.
Yeah, absolutely. Good question. Any other questions? All right, cool. Well, this meeting has been recorded, so you'll have you guys should all have access to this video. I'm not entirely sure if it'll be on YouTube. I think maybe, but this is recorded, and yes, these slides are available to share. So you guys will also have a copy of these slides. Just keep in mind when you're copying and pasting from PowerPoint, sometimes it doesn't. Sometimes the tags or the dashes don't really translate very well. So that may cause some errors in your terminal. With that being said, I guess this talk is over. So I wish you all a happy Friday. And again, if you have any questions, visit the HPC website, submit a help request, ticket, anything. So, all right. Well, thank you guys.
Thank you, Randy.
Yeah. Thanks, Robbie, for juggling those questions in the chat. Megan, thank you for co-hosting. All right. Yes. Have a good weekend.
Thank you, Randy.
Oh, yeah. No problem, John.
Thanks, Randy. Appreciate it.
Oh, thanks, DJ.